Good morning. This is the course on Introduction to Probability Theory and Statistics, and we are in topic 10, estimation, and already we covered two lectures, one on point estimation, definition and properties and few examples, and in the lecture 2 we have discussed two important methods of finding the estimator, that is a method of moments and a method of maximum likelihood. And one or two examples also we have discussed in that lecture 2. Now, we are going to discuss interval estimation in lecture 3. The brief introduction about the estimation which I have given in the beginning of lecture 1 of topic 10, estimation. There I have given what is the meaning of estimation and when do you need a estimation is needed in the statistical analysis and so on. Followed by that we have discussed in detail about the point estimation. The process is called estimation, and whenever the parameters of the populations are unknown, you can estimate those parameters using the sample, and that process is called estimation. And the function which you create with the help of random samples, that random variable, that is a statistics, and that is going to be called it as a estimator for the unknown function of a parameters of the population. So, the most common point estimators are the sample mean and the sample variance. But the difficulty is when a sample is drawn, it is unlikely that the value of a point estimator is equal to the true value of the unknown parameter theta. It is very difficult to conclude the estimator which you got it, that is going to be the equal to the true value of the unknown parameter. That is what I have given in one example also. If you recall, there is a class of 70 students. You are interested to know the population mean or the class average. By asking a few students marks, you calculated the sample mean, and that sample mean may not be equal to the true value of the population mean. So, that is a disadvantage with the point estimator. You got the sample mean by asking a few students marks, then you made the average out of it, that is a sample mean, but the sample mean may not be the same as the true value of the unknown parameter, that is the unknown population mean. I am just giving one example, like that you can think of many more examples. And also when you have a population follows a continuous type random variable, when the distribution of the population follows a continuous type random variable, then you know that the probability of the estimator taking the one value, any value, that is going to be 0. Therefore, it is meaningless when you compute the point estimator for the unknown parameters of the population distribution. In that scenario, you can find the range in which the values can lies of the unknown parameter of the population with the appropriate probability, because once you say the range, in what logic you identify the range, that is the question. So, you can assign appropriate probability to say in this range with this much probability the unknown parameter values can lie. Again we are using the same approach of using the random samples. You are identifying the estimator of the unknown parameter, but not one value, you are giving a range in which the values is going to lie. Therefore, it is going to be called as the whole process is going to be called as a interval estimation, and whenever you discuss about the interval estimation, you have to give appropriate probability, or we call it as a confidence limit, in which you are saying the range in which the interval, the range in which or the interval in which the unknown parameter values will lie, that is going to be the interval estimation of the unknown parameter. So, with this brief we are moving into the first important concept of interval estimation for the unknown parameter, that is a population mean, with some confidence limit, we call it as a confidence interval. So, the theorem says if x bar is the sample mean of size n from a normally distributed population with the known variance sigma square and unknown mean mu. That means what we are saying is the population follows normal distribution with the parameters mu and sigma square. You know mu is a population mean and sigma square is population variance. Additional condition we are making, the mean is unknown, whereas the variance is known to you. The sigma square is known, whereas the population mean is unknown. Obviously, you can immediately make out the sample mean is going to be the point estimator for the population mean mu. But now, we are going to give the interval estimation for the unknown parameter, which is population mean, with the 1 minus alpha 100% confidence. That means, if you give the value of alpha, alpha is always lies between 0 to 1, then you can say I can able to conclude the interval estimation or confidence interval for the unknown parameter mu is going to be this much interval with 1 minus alpha 100%. That means, you have to supply alpha. After supplying the alpha value, that means by varying the alpha value, obviously you will have the different range or interval in which the mu is going to exist. So, this is the interval estimation of mu, where mu is unknown. Whatever it is written here, x bar is the sample mean and sigma square is the population variance. So, sigma is the standard deviation of the population and n is the sample size, and there is another notation which is used, z of alpha by 2. That means, the point in which the right tail probability of a standard normal distribution, the probability is alpha by 2. So, we are denoting the point in which the right tail probability is alpha by 2 for a standard normal distribution, that is denoted by z alpha by 2. So, how we can get this result, that I am going to derive it. Once we have given the derivation for this, then later we are going to relax one by one and we are going to find out the confidence interval for many more unknown parameters and so on. The concept is the same. So, therefore, I will go giving the proof of this theorem, whereas all the other results goes in the same way. So, let me start with the how to prove this confidence interval is for the population mean is this much with the given alpha or with the 1 minus alpha 100%. So, let us start with the population follows a normal distribution with the mu and the variance sigma square, and you should remember mu is unknown. Therefore, we are going for estimation for the population mean mu and the sigma square which is known. We are going to relax this also later. We are going to make it sigma square is also going to be unknown later. First, let us give the confidence interval for the population mean. Since the population follows a normal distribution with the mean mu and the variance sigma square, each sample follows a normal distribution with the mean mu and the variance sigma square. And we have n samples. Therefore, all the xi's are IID random variables, mutually independent as well as identically distributed random variable, all those n random variables. Since we are working for estimator for the population mean, which is mu is unknown, you know that the x bar, which is 1 by n summation x I is equal to 1 to n, this is going to be the sample mean, and which follows the sample mean follows a normal distribution with the mean mu and the variance sigma square by n. This part we have done it in the topic, the previous topic as a sampling distribution. This derivation we have already done it. Whenever the population follows normal distribution, then you can conclude the sample mean sample mean follows a normal distribution with the mean mu and the variance sigma square by n. Once I have a normal distributed random variable, then I can standardize by subtracting the mean divided by the standard deviation of x bar. So, this is going to follow standard normal distribution. Z is going to be a standard normal distributed random variable. Now, what I can do is a very important concept. Whenever the psi of z, if I define it in the form of 1 divided by square root of 2 pi integration from minus infinity to z e power minus t square by 2 dt. This is nothing but the probability of lies between z less than or equal to z, small z, where capital Z is the standard normal distribution. So, I can write the using the psi of z, I can make out the probability of x bar minus mu divided by sigma by root n lies between minus z to plus z. That probability is same as the probability of x bar minus mu divided by sigma by root n lies between minus z to plus z. That is same as, if you do little calculation in terms of z, you can able to get that is 2 times of psi of z minus 1. So, what I can do, take this value is equal to alpha. I can take this value is going to be alpha, this value is going to be considered as the, I made a mistake. This value I can take it as 1 minus alpha. That means a probability of x bar minus mu divided by sigma by root n lies between minus z to plus z, that is equal to 1 minus alpha. Then I can rewrite this result as probability of z, instead of z I can use only x bar, because I need the x bar quantity. X bar minus mu divided by sigma by root n lies between minus z to plus z is equal to 1 minus alpha. I can do little calculation inside. I can rewrite this is same as probability of mu lies between x bar, or I can write it in the capital letter, x bar plus z alpha by 2 sigma by root n, and in the left hand side it is x bar minus z alpha by 2 sigma by root n. That means this probability is going to be 1 minus alpha. If I nicely draw the same scenario in the graphical way, I can show the graph that is in the next page. Yes, that means if I denote the point in which the right tail probability is alpha by 2, that means this point is going to be z alpha by 2, and this point is going to be minus z alpha by 2, because it is a standard normal symmetric. Therefore, the probability lies between minus infinity to minus z alpha by 2, that is alpha by 2, and similarly probability of z alpha by 2 infinity, that probability is going to be alpha by 2. Therefore, the tail probabilities are going to be alpha. Therefore, the mu lies between this quantity is going to be 1 minus alpha. That means the non-shaded region, that probability is 1 minus alpha, and the probability alpha is divided into two equal parts, that is alpha by 2 in the right tail and alpha by 2 in the left tail. Therefore, whatever I have derived, that is the mu lies between this interval, that is going to be 1 minus alpha by 1 minus alpha. The probability of mu lies between this interval, that probability is 1 minus alpha. That means I can say it is 1 minus alpha 100 percentage, 1 minus alpha 100 percentage. The confidence interval for mu is small letter, that means it is a value, small x bar minus z alpha by 2 sigma by square root of n. Everything is known, sample mean, and this is the point, and sigma square is known, therefore sigma is known, n is known, comma x bar plus z alpha by 2 sigma by root. This is the confidence interval, square root of n. So, this is the confidence interval for mu with the 1 minus alpha 100 percentage. And you see that this interval is the random interval. That is very important observation. The interval is not fixed, because it is a function of sample mean. So, whenever you take any random sample, your sample mean is going to be random. So, this interval, since x bar is the sample mean, that is a random, whereas population variance is known, sample size is known, and for a fixed alpha, this z alpha by 2 is a fixed value, whereas the small x bar, that is a sample value which is random, or capital X bar, that is a random variable. Therefore, this interval is a random interval. Even though you fix the alpha and other values are fixed, and this is the random interval for the unknown population mean mu with the 1 minus alpha 100 percentage. So, this is what we are trying to prove in this theorem. So, what the theorem says, the mu is lies between this interval with 1 minus alpha 100 percentage. That means the probability of mu lies between this interval is equal to 1 minus alpha, both are one and the same. where z alpha by 2 means the right tail probability is alpha by 2. That means we are finding the random interval for the unknown population mean mu with the given 1 minus alpha 100% confidence. Therefore, this is called the confidence interval for the population mean that is given in this theorem. Fine. Now, we are coming into relaxing the condition of the population variance also unknown. That means you cannot use the earlier derivation, because the earlier derivation uses the population variance is known. That means you have to look for identifying another statistics which can replace the population mean by the corresponding estimator. And you know the sample variance is the estimator for the population variance. So, whenever the population variance is unknown, you can use sample variance as the estimator for the population variance. Therefore, you can create a new statistics, that is x bar minus mu divided by s square root of n, s divided by square root of n. That means instead of the population standard deviation, you use sample standard deviation. Obviously, the earlier derivation goes x bar is a normal distributed with the mean mu and the variance sigma square by n. Therefore, you use the statistics that is z is x bar minus mu divided by sigma by root n, which is the standard normal distribution. You cannot use that statistics. Now, you have to identify another statistics, that also I have explained in the sampling distribution, that is x bar minus mu divided by s divided by square root of n. That is the t distributed random variable with n minus 1 degrees of freedom. So, you take that as a statistics as a starting point. Then once you have a t distributed random variable with n minus 1 degrees of freedom, you take a probability density function of a t distribution. For a given alpha, you keep 1 minus alpha probability. This is also symmetric one. Therefore, if you do the derivation in the same way, you will get the probability of mu lies between this interval, that is going to be 1 minus alpha. Instead of a standard normal distribution, you will have a t distribution probability density function. You shade the region, the right side you will have alpha by 2, left side you will have alpha by 2, and that point is denoted by small t n minus 1 comma alpha by 2, because this probability density function is with respect to the n minus 1 degrees of freedom, and the point is chosen with the right tail probabilities alpha by 2. Therefore, and since it is again symmetric, therefore, the minus of that means it is in the left side, and so on. Again you will have the same derivation. Instead of standard normal distribution, you have to use the t distribution with n minus 1 degrees of freedom to conclude. That means now we are giving a confidence interval for the still unknown parameter mu only, but for the unknown parameters of mu as well as sigma square. Therefore, the sigma square is replaced by s square, that is a sample variance. So, here we are using the standard deviation of sample standard deviation, and all other values are known. That means by varying the alpha, you will have the different intervals, and still the interval is a random interval, that also you should remember. There is a simple problem how one can find the 95% confidence interval using the theory which we have discussed. So, you can go through this example and you can identify what is the interval in which the 95% confidence in which you will get the interval. I have given the problem as well as the solution, you can go through and understand. I do not want to repeat the same thing. Similarly, there is another problem also we have explained, and here we have used the t distribution, and you can identify what is the point in which the right tail probability is alpha by 2, that you can by seeing the table you can make out. Any table anywhere you can identify the t distribution table, and for a given degrees of freedom you can get the values and you can verify this. If at all any mistakes, that can be corrected, because we are revising some of the draft here. So, if at all any other mistakes are there, that you can fix it. We will, once we identify this is a typos, then we will fix it immediately. So, till now we have discussed with one population, now we are coming into two populations. So, you can do the same exercise for the interval estimation for difference of two population means who are unknowns. If they are known, you do not need to find out the estimation at all. So, all those things started with the unknown parameters. So, the mu 1 and mu 2 both are unknown, and you are estimating in the form of interval with the given 1 minus alpha 100% confidence. You know the theory. Once you have a normal distributed random variable, if they are independent, then whether it is sum or difference, that is also going to be again normal distributed. Therefore, whatever the earlier theory for one population, you can use the same logic for the two populations also, because both are independent populations, and you can use all the theory to conclude the same thing. So, the derivation is almost same, only thing is instead of one random variable, you have now difference of the two random variables, again that is also normal distributed with the mean mu 1 minus mu 2, and you know how to compute the variance of two normal distributed random variable when it is a difference, that is going to be sum of their variance, correct. So, apply the same theorem with the difference of the sample mean random variable, then apply the same thing, you will get the interval estimation for mu 1 minus mu 2. That means the probability of mu 1 minus mu 2 lies in this interval, that is 1 minus alpha, correct. Here the n1, n2 are the sample size for the samples taken from the first population as well as the second population respectively. Again you will have a remark, suppose the population variance are also unknown. First we started with only population means are unknown, whereas you know the population variance. But suppose population variance is also unknown, then you can get the pooled sample variance, that is S suffix p square, the p for pooled, that is n1 minus 1 times the sample variance of the first one plus n2 minus 1 sample variance of the second population S2 square divided by n1 plus n2 minus 2, because everywhere you will end up with n1 minus 1 degrees of freedom for the first one and n2 minus 1 degrees of freedom for the second one, the t distribution. Therefore, you will end up with the n1 plus n2 minus 2 degrees of freedom of t distribution. So, the same theory, instead of a standard normal distribution, you will have a t distribution with n1 plus n2 minus 2 degrees of freedom, and keep the right tail probability alpha by 2, left tail probability alpha by 2 because of the symmetric nature. So, the interval in which mu 1 minus mu 2 lies, that probability is 1 minus alpha, correct. So, the derivation is the same as what you have done it earlier with the one population. Instead of that you have two populations, but you go for difference of the two random variables, again you will have the same conclusion. Yeah, there is a simple problem for see this example. The population follows a non-normal distribution and you know the variance, and the question is how large must the sample size be so that the length of 95% confidence interval for the mean is 1.96. So, it is sort of a not a given sample size, you are finding the confidence interval. Here the question is what is the sample size so that you will get this much confidence interval for the population mean, which is unknown, and the length of the interval is 1.96. Earlier we discussed the range of the unknown parameter, which is for the population mean or whatever it is. So, the length is 1.96 is given. So, you have to identify what is the sample size. So, you can easily able to compute the interval is x bar minus sigma by root n to x bar plus sigma by root n. Therefore, the length is going to be 2 times, there is a mistake here, it is sigma here sigma sorry z alpha by 2 is missing. So, the mistake is here, it is there is a mistake, x bar minus z alpha by 2 this much comma x bar plus z alpha by 2 sigma by root n. Therefore, the length is going to be 2 times z alpha by 2 square root of this or sigma by root n, you can think of. So, therefore, the length is so you can identify the length is going to be 1.96, you can equate therefore, the length of the interval is given, and in the problem is started with the length is given, that is 1.96, but for in this problem because of the 95%, the point in which your probability right tail probability is going to be alpha by 2, that point is also 1.96. Therefore, you equate and identify what is the value of n in which you are going to satisfy this equation. So, that n is going to be 100. That means, if you take a sample of size 100, then the whenever the population mean is unknown and population variance is known, then you will get the length of the interval is going to be 1.96 with the 95% confidence, correct. With the 95% confidence, the length of the interval is going to be 1.96 for a known variance, and the sample size has to be 100. Now, we are coming into the estimator for the unknown parameter, which is population variance. That means, whenever the population variance is unknown, immaterial of whether the population mean is known or not, that we do not need to worry about it, because that does not involve here. Whenever the population variance is unknown, then you can get the point estimator, that we have already discussed. The sample variance is going to be the point estimator for the population variance. but with a given 1 minus alpha 100% confidence, you can get the interval estimation or interval estimator for the population variance, that is n minus 1 times s square divided by, that is nothing but the right tail probability for a chi-square distribution with 1 minus with n minus 1 degrees of freedom, that is a point is denoted by chi-square alpha by 2 comma n minus 1, it is just notation, and the right side interval is n minus 1 s square divided by chi-square 1 minus alpha by 2 comma n minus 1. We will not use the notation like standard normal distribution, like t distribution, because both are those two are symmetric distribution. Therefore, you can easily represent the right tail probability and the left tail probability with the one point with the minus sign, but here the chi-square distribution is not a symmetric one. Therefore, whenever you say the right tail probability is going to be alpha by 2, then you will have one notation, and when I say 1 minus alpha by 2, that means the point in which the right tail is 1 minus alpha by 2, that is denoted by chi-square of suffix with 1 minus alpha by 2 comma n minus 1. So, maybe I can show the graphical representation, 1 minute. So, I can go to the yes. So, I can take a new page. So, for this problem the derivation is similar to the earlier derivation. We started in the earlier derivation, the x bar is normal distributed with the mean mu variance sigma square by n. Therefore, you made a standard normal distribution, then you have a probability density function of a standard normal distribution, then you partition alpha by 2, therefore, you got in the middle 1 minus alpha probability. The same way you should do it here, you should take a chi-square distribution with the n minus 1 degrees of freedom, the probability density function of chi-square distribution with the with n minus 1 degrees of freedom. I am just drawing a rough diagram. Okay. So, if at all any mistake you correct me. So, here the statistics which you want to take, that I can keep it as the some letter d, that is n minus 1 times s square by sigma square. This follows a chi-square distribution with n minus 1 degrees of freedom. So, the way we started standard normal distribution, x bar minus mu divided by sigma by root n, that is a standard normal distribution. The same way here the statistics is n minus 1 times s square by sigma square, that follows a chi-square distribution with n minus 1 degrees of freedom. Therefore, we are identifying what is the point in which this probability is alpha by 2. So, this is denoted by the way I am using now, it is alpha by 2 comma n minus 1, correct, and the point in which I am getting another alpha by 2 in the left side, that is this point is denoted by chi-square 1 minus alpha by 2 comma n minus 1. That means this probability is alpha by 2, therefore, the right probability is going to be 1 minus alpha by 2, correct, and this point is denoted by chi-square of 1 minus alpha by 2 with the n minus 1 degrees of freedom, whereas this point is denoted by chi-square of alpha by 2 comma n minus 1. So, the middle part, so basically what I am saying is if I denote some point is chi-square of alpha by 2 comma n minus 1, that means the right of that point the probability is alpha by 2, that is it. Therefore, this point is going to be denoted by chi-square 1 minus alpha by 2 comma n minus 1. So, therefore, this results comes from starting with n minus 1 s square by sigma square, that follows a chi-square distribution with n minus 1 degrees of freedom. So, therefore, you apply that statistics and you partition the whole probability by alpha by 2, alpha by 2 and in the middle 1 minus alpha. Therefore, you will get the probability of lies between that particular statistics, that is n minus 1 s square by sigma square, between that interval is 1 minus alpha, but we are looking for confidence interval for the sigma square and the sigma square comes in the denominator. Therefore, you have to rearrange it, therefore, you will get the interval is going to be this interval with the 1 minus alpha 100%. So, there is a very simple problem in which you have a samples taken from the normal population and sample size is 13 and instead of each sample is provided, we have provided these two informations. So, using that we are trying to find out what is the confidence interval for sigma square with the 1 minus or with the 90%. So, you can find out the sample mean, you can find out the sample variance, then you can identify what is the point in which your right tail probability is going to be right, both right and left side probability is going to be 0.1 because it is a 90%. Therefore, the one side you should have a 0.05 and the other side you should have a 0.05. So, you identify the point, then you get the interval. So, this is the confidence interval for sigma square using the theory which we have just now discussed. Let us consider this example. The mean and standard deviation for the quality grade point average of a random sample of 36 college seniors are given to be 2.6 and 0.3 respectively. That means, the mean value is 2.6 and the standard deviation is 0.3 and the sample size is 36. So, the question is find out 95 as well as 99% confidence intervals for the mean of the entire senior class. The given information is sample mean 2.6 and the sample standard deviation is 0.3 and the size of the sample is 36 and the question is find the 95 as well as 99% confidence interval for population mean mu. So, first you try to compute what is the confidence interval for 95% interval for mu. After substituting all the values, you will get the interval, and similarly so the 95% confidence interval is going to be between 2.5 to 2.7 for the population mean. Similarly, you work for 99% confidence interval, that reduces to 2.47 to 2.73. For the same problem, we are finding the two different confidence interval for the population mean, one with the 95%, another with 99%. The conclusion is we see that a longer interval is required to estimate mu with the higher degree of accuracy. That is the conclusion. The same way, if you have two different populations, when they are unknown, then you can be able to get the interval estimation for ratio of population variance which are unknown. There is no meaning of difference of population variance. You can do the difference for the population mean, not for variance. You can go for a ratio of two population variance which are unknown. For that you have to first create the statistics. the way you started the creation of strata 6 with the standard normal, then t distribution, recently chi-square distribution. For this problem, first we have to create the strata 6 which is related to the ratio of two different random variables and so on. You will end up with the f distribution. You will land up with the f distribution in a nice way. Then once you identify f distribution with the degrees of freedom is mu 1 n 1 minus 1 and n 2 minus 1, then you get the probability density function of a f distribution, which is also not symmetric. You keep alpha by 2 is the right tail and alpha by 2 in the left tail, and identify the point in the f distribution, so that the probability of lies between that strata 6 going to be 1 minus alpha. Again you will not have a sigma 1 square by sigma 2 square easily. So, you have to rearrange the terms inside the probability, so that finally you will get the sigma 1 square divided by sigma 2 square, the interval in which it is going to be this much is 1 minus alpha. So, whatever we have done the derivation of first one, you have to do the same concept for the chi-square distribution, t distribution with the f distribution for the different problems related to the estimations with the same 1 minus alpha 100 percentage. So, we are not changing that, but we are changing the unknown parameters. First we started with the only population mean, then we land up with the difference of the population mean, then we taken population variance is unknown, but still you are interested to find the population mean only. Then we land up only the population variance, then the ratio of the population variance. So, there is a very simple example how one can find the confidence interval for sigma 1 by sigma 2. So, our derivation is sigma 1 square divided by sigma 2 square. So, the same logic can be applied for the after you get the confidence interval for sigma 1 square divided by sigma 2 square, you can get the confidence interval for sigma 1 by sigma 2 by taking a positive square root of that interval. That is all. All other things are informations are there. You have a sample of size n1, sample of size n2 is given and so on. So, you can apply the theorem and get the result. So, now we will discuss the review problems on topic 10. Go through the question carefully. The point estimate is dash used to estimate the parameter. There are 4 options: any value from the sample, a sample statistics, error margin, random number. Go through the question carefully, and the correct answer is out of 4 options. So, the correct answer is the sample statistics is used to estimate the parameter. Second question, as a result of central limit theorem, if all samples of size n which is greater than or equal to 30 are obtained, then mean of a sample mean of the sample mean equals the population mean mu. So, we use the notation mean of the sample mean is a expectation of x bar. Expectation of x bar is equal to mu, due to the fact that the mean of the sample distribution equals the population mean, x bar is referred as, there are 5 options, only one option is the correct answer. Whether it is a biased estimator or it is going to be called it as unbiased estimator or random estimator or controlled variable or it is just a parameter. So, used on based on the information which is given in the question, it is going to be called it as a unbiased estimator. Now, we will move into the third question. Which one of the following options best describes the upper bound of the confidence interval? There are 3 options, out of that only one option is the correct option. Option A, point estimate, option B, point estimate minus the margins of error, option C, point estimate plus the margins of error. So, the correct answer is a point estimate plus the margins of error. Question number 4. The term 1 minus alpha refers to the level of significance. Is it true or false? The statement is given whether this statement is a correct statement or incorrect statement. It is a false statement, it refers to the level of confidence. The 5th question, the population mean has a 95% confidence interval of 75.29 to 81.45. If the confidence level is dropped to 90%, the confidence interval will, there are 5 options, out of that which option is the correct one? With the 95% confidence interval, the interval is given. When you reduce it into the 90%, whether the interval, what will happen, whether it become narrow or stay the same, get larger, more than the double in size, or most likely no longer contain the population means true value. So, which is the correct answer? The correct answer is it becomes narrow, the interval becomes narrow when you reduce the percentage from 95 to 90. The 6th question, the range of a test statistic Z is, there are 4 options, whether it is from 0 to 1 or minus 1 to 1 or 0 to infinity or minus infinity to infinity. Which is the correct option? The correct option is The range of the statistic z is minus infinity to infinity. So, till now we have discussed in this lecture 3 how one can get the confidence interval for the unknown parameters of the population. In particular, what we have done only the population mean when population variance is unknown, then difference of the population mean and population variance, then the ratio of the population variance. You can use the same thing for ratio of the population standard deviation also by taking a positive square root of the results which you got it for the ratio of the population variances. These are all the important interval estimations with respect to the population parameters. There are many more, but since this course is introductory level, therefore, we are stopping with the population mean as well as the population variance, not more than that. With this, let me stop the lecture 3 of topic 10, that is estimation. In the next topic, we will discuss about the hypothesis testing in detail. Thank you.